All right, welcome back to the next week of online Chem 110. You guys have an exam upcoming in a week and a half. Last session we covered titrations. I hope those are going well. Again, if you notice, they are pretty much the same problem repeated. It just depends on the weak base or weak acid and what you're titrating with. So again, please reach out for any questions on those. This week I'd like to cover KSP and the introductory part to thermodynamics. So thinking about entropy of the universe and spontaneity of certain reactions. So we're going to go ahead and start right in. So we have a problem here. It says calcium ions are found in hard water and stearate is a subcomponent. The solubility of calcium stearate is 0.004 grams per 100 milliliters. What is the KSP? Well, first, the solubility is 0.004 grams per 100 milliliters. Normally, we think of solubility in grams per liter or grams per milliliter. So let's go ahead and convert the solubility to start right away, just so we can get units correct. So we're going to start with 0.004 grams per 100 milliliters. That was what was given to us in the problem. Now we want to convert that. Let's go ahead and convert that to, let's say, grams per milliliter. So I would divide this number, 0.004, divided by 100, right? Because then that would cancel out this 100. So if I divide this by 100, that 100 cancels out, and this becomes 0.004 divided by 100, which is 0.00004 grams now per milliliter, right? The 100 divided by 100 would be 1 milliliter. But we want it in grams per liters, so this we would have to multiply by 1,000 because there's 1,000 milliliters in a liter, and multiply this by 1,000. So we would get 0.04 grams per liter. So that's our solubility. Again, I didn't do anything with the math. I just adjusted this 0.004 grams per 100 milliliters, 2 grams per liter, because that's what we normally work in for units of solubility. So now let's set up an ice table. Again, the ice table, as you guys found in Unit 3, you did almost every problem. We're going to be doing ice tables a lot in Unit 4 up to thermodynamics. So anything with K. In this case, we have KSP, so we probably want an ice table. So let's go ahead and set it up. What's my reactants? Well, we know it's water because it's a solution. We know water doesn't do anything in equilibrium. So we have calcium stearate. Again, it's an enormous molecule, but don't worry too much about that. Why it's that big of a molecule, it won't adjust anything. And then what is this going to go to? So if this were to break up into constituent ions, what would we make? Well, we have calcium, and what's the charge on calcium ion normally? 2+, right? We get that from the periodic table. Calcium has a 2+ charge as its normal ion. This would be aqueous. Again, this would be aqueous, or this would be a solid. I forgot to write that. Again, it's a hard water component, so hard water is solid. And then calcium 2+ ion would be aqueous from the solution. And then what would be our other product? Stearate, which is C17H35COO2, and we have 2 of them, right? Because this has a -1 charge total, so we have 2 of them to cancel out the 2+. So we have 2 stearates. So 2 C17H35COO2. So now we have our balanced chemical equation. Solids don't do anything in equilibrium, right? We never did anything with a solid or a liquid. So in that case, nothing will occur. Stearate is aqueous. We start with 0 on both. What's significant about my change value in the ice table? Oh, we have a 1 and a 2. So I'm adding 1 equivalent of x here, and I'm adding 2 equivalents of x here, right? Because we have stoichiometric coefficients of 1 and 2. Again, stoichiometry still applies because we're looking at a k value. So now we have x and 2x. You may also see the x value in some chemistry textbooks as s. Again, it's just a placeholder for a number, x or s. So this would be 2s because we're working with solubility now instead of concentrations, working with the solubility. So S would make sense, but I will use X from here on out just because that's how we've been doing it in the previous. So we have KSP is equal to products over reactants. Well, we have X and we have 2x squared. Again, going back to ice tables in unit 3 with acid-base equilibria, do not forget we have the 2x, then you have to square it, right? 2 coefficient would mean a 2 here. And we're solving for KSP, so we're solving for this value. How are we going to get x? Think about that. How would we get x from this equation? Well, we have to consider the solubility that was given to us. In this case, we have a solubility of 0.04 grams per liter. Well, the molar mass of this would give me a gram value, right? So let's calculate the molar mass. Again, this is Chem 109 review, calculating molar mass. If you did the molar mass right, you should have gotten 607.02 grams per mole. Okay, so I have 0.04 grams, and then in 1 mole, I have 607.02 grams. So grams cancel, and I now have, let's round, 6.6 times 10 raised to the -5 moles per liter. Okay, so how does this value, 6.10 -5, fit into our ice table? Well, the 6.6 10 -5 is just another solubility value, right? Moles per liter, grams per liter. It's something, some sort of unit of mass, which in this case would be moles, divided by liters. This just equals X. Or if you're working with S, this equals S. So if this just equals X, we can plug this 6.6 -5 in for each X. So our KSP would be 6.6 times 10 raised to the -5, 2 times 6.6 times 10 raised to the -5 squared. So now we have this is all just one number, and we have a KSP value equal to 1.14 times 10 raised to the -12. Again, kind of tough because you have to convert right away to grams per liter, run your ice table like normal, do K is equal to products over reactants. In this case, our reactants was just a solid, so we only have products. And then use the 0.04 grams per liter. In this case, I had 0.04 grams. We know the molar mass. Convert to moles per liter. Recognize that's a solubility. Plug it in and solve. Again, it's very straightforward, but if you got a little confused, it was probably right here. That's okay. Get used to seeing moles per liters and grams per liters. They may show up on your homework and on future exams. All right, let's go ahead and move on. All right, so now we have, will barium chromate precipitate when a 12.5 milliliter of 0.14 molar barium nitrate solution is added to 550 milliliters of a 0.0216 molar sodium chromate solution? And I gave you the KSP for barium chromate. I would encourage you to pause the video and work this one out by yourself. And then you can always use me for extra help if you need it when working the problem. So go ahead and pause, get started, and then I'll start working. Okay, so for those of you who have not paused the video or are coming back, we're going to go ahead and work out the problem. What's the first step? Write our balanced chemical equation. So I have barium nitrate, which again, barium is 2+, so I need 2 nitrates, aqueous, plus sodium chromate, aqueous, is in equilibrium with barium chromate, solid, and 2 NaNO3. And sorry, it's a little tight there, aqueous. So we now have a balanced chemical equation. But now I need to think about what I'm going to do for my ice table. So let's think about that. So I have, whenever we have a K, if you look back at the last problem, it's a very similar approach with ice tables. You have what you're looking for relative to K, and then what it dissolves into. So the solid and what it dissolves into. So if you look at our balanced chemical equation, barium chromate is our solid, right? So let's start there. Barium chromate, again, +2, -2 charge. There's no extra exponents needed. What is this going to dissolve into? Barium 2+, aqueous, and chromate 2-, aqueous. But we really don't know the way our chemical reaction is going to go, right? We have this first reaction, and now we have this. But which way is this going? Well, if you don't know, we can always look at Q and compare that to K, but we need to look at the concentrations of each first. So let's look at barium 2+. Let's start with the barium ion. So we know it's 0.145 molar, right? It's given to us in the problem. 0.145 molar times, well, 12.5 milliliters. I'm going to convert that to liters right away. 0.0125 liters is equal to 0.0018 moles. So I know I have 0.0018 moles of barium 2+. So now let's find the concentration of barium 2+. I know moles, now I need to find total liters, right? Because we know a concentration is molarity, which is moles per liter. So my total volume or total liters would be what? Well, I have 550 milliliters plus 12.5. So in a liter value, that would be 0.5625 liters, right? Or 562.5 milliliters, right? I just add the 12.5 and 550 to get my total solution value. So now I have moles and I have liters. Let's go ahead and find molarity. Moles divided by my liters. And my molarity of barium 2+ turns out to be 0.0032 molar. Great, so now we have one of those. Now let's find the other one. Well, we need chromate. So let's do chromate right below it. CrO4, 2-. It's the same exact approach. 0.0216 molar sodium chromate. So 0.0216 molar times 0.55 liters, because we have 550 milliliters of that 0.0216 sodium chromate solution. So we take molarity times liters and we get a mole value, which in this case turns out to be 0.012 moles of chromate. Same process, 0.012 moles divided by 0.5625 liters, because again, we have the same liter value, right? We didn't add any more or less in the second part. It's always going to be 562.5 milliliters or 0.5625 liters. So we find our moles, or molarity, excuse me, to be 0.0213 molar chromate. So now we have a barium 2+ molarity and a chromate molarity. What are we going to do? Well, if you want, we can take a look at the ice table, but what do we notice? Everything's 1-to-1. So if I were to set the ice table, we'd have 0, 0, plus x, and then x and x. I'm not going to do the ice table because you guys should realize it's 1-to-1. So then we just need to take 0.00 k is equal to 0.0032 times 0.0213. Is this correct? If I'm asking if it's correct, it's probably not. This is where I am wrong. If you wrote k is equal to 0.0032 times 0.0213, you're not technically 100% wrong, but I already gave you the KSP. If I gave you the KSP, you can't solve for a new k. What are you solving for? You're solving for q, right? This brings back Unit 3 memories. So if we solve for q here, we get a q value of 0.1234 zeros 683 molar. So our q value is equal to 0.0000683 molar. What was the question asking? Will barium chromate precipitate? Well, I have a K and I have a Q. In this case, Q, which is to the -5th, is much greater than K, which is to the -10th. So let's write that down. Q is greater than K. Again, all of this was to solve for Q. I was given a K. We are now comparing Q, which is 10 raised to the -5th, versus K, which is 10 raised to the -10th. Q is obviously much bigger by 5 exponents than K. So Q is greater than K. Precipitate will form. When you're doing Q and K problems relative to KSP, if Q is greater than K, precipitate will form. If K is greater than Q, precipitate will not form. So again, working through this problem, we had an overall chemical equation just to make sure we were on the right pace. We set up our initial ice table. We solved for initial molarities. Everything was 1 to 1. So we know whatever our initial molarity is, that's our final, because it's 1 to 1, 0, 0, plus x, then these two values. Solve for Q, then compare Q and K. It's a really good problem to know for homework, especially. Great, moving on. In which would iron hydroxide be most soluble? In which of these three solutions would iron hydroxide be most soluble? I encourage you to pause the video and think about it. So, which one is the most soluble? We want to remove, or I guess neutralize, the OH, right? Because Fe OH2 is a solid. That's horrible. Sorry if you can't read that. FeOH2, there we go, is a solid. Which one is it most soluble? Well, if it's a solid, it's going to break up into Fe2 plus and 2OH minus, both aqueous. The solid breaks into its ions. So if we want this to be the most soluble, we want a solution that favors reaction with these. Well, we look back at acid-base chemistry, we notice we have two OH minuses. We have Fe2 plus, obviously, that's the metal ion. We're not worried too much about the metal ion here. We're more about the OH minus. What reacts well with OH minus? Well, we know OH minus makes things such as NaOH, CaOH2, and so on. What are these two? Very strong bases. So if we have strong bases here, what do we need to neutralize those strong bases? A strong acid, which would be 0.5 molar HCl. These might do a little bit of solubility, but HCl is going to react big time with OH minus because, again, we know OH minus is a major component of strong and weak bases. If we need something to react with a base, we pick an acid. That's how you would go about solving this problem. Okay, that's kind of a multiple choice problem that you may see in the near future. Also, kind of a multiple choice problem, or select the answer. Select the substance with the greatest entropy. So now we're moving away from KSP and going into entropy. So what do we know about greater entropy? We're looking for the greatest entropy. Entropy means order or disorder. Entropy is equal to disorder. So when you look for something with a lot of entropy, you're looking for something messy. You're looking for something with a lot of different components, a lot of different scattering. It's something that's not ordered. Because dystropy, the opposite of entropy, means order. So dystropy is order, entropy is disorder. So let's take a look at neon gas versus helium gas. Which one of these is going to have the greatest entropy, or in other state, which one of these is going to have the greatest disorder? Well, they're both gases, so we know the ions are both going to be spread out, right? Because we know ions like to spread out in a gaseous form compared to a solid form where they're packed together. So they're both gases, so we can't really look at the phase. What about neon versus helium? They're both noble gases, but neon is further down the periodic table, right? Neon is, I believe, 18. You can check me on that. And helium is 2. So neon has a greater molar mass, which means more opportunities to scatter. So neon is going to have the greater entropy. Again, we always want to look at the phase first. If it's a gas, it's going to have the most entropy, right? Because gas ions want to spread out. If we have a solid, they're packed in. But if we have a gas, I'm just going to write solid. If we have a gas, these molecules are going all over the place. So we need a gas. In this case, we have 2 gases. This one has a larger molar mass, so that means there's more atoms to spread out. If we have more atoms spread out, that means greater disorder, which means greater entropy. Let's look at option 2. C12H22O15 as a solid, or C12H22O15 as an aqueous. It's the exact same organic molecule. One's a solid, one's aqueous. Which is going to be more disordered? The aqueous, right? We think about aqueous as a liquid most of the time because it's a solution, right? Aqueous means it's in water. So if we have a liquid versus a solid, we know the liquid molecules or liquid atoms are going to spread out more than the solid. Great. CH3CH2OH as a gas, or the same thing as a liquid? Well, we already answered that. We know it's the gas because gas ions can spread out more and have greater disorder than the liquid. So all I'm trying to get you to think about here is order versus disorder and kind of periodic trends and phase trends. Okay, last question for the day. This one's tough. Feel free, once again, as always, to pause the video and work this out by yourself. For those of you who are just latching on to thermodynamics, this is going to be really tough. But I would highly recommend that, I don't know, about Wednesday or Thursday of this coming week, you come back and you work this problem. It's a really good problem, I think, for review, and you should be able to solve this for the upcoming exam. So go ahead, pause the video, try to solve it if you think you're ready. Okay, so imagine 15 grams of ice at 273 Kelvin, or 0 degrees Celsius, is placed at 298 Kelvin, which normally assumes room temperature. Calculate change in entropy of the universe. And I gave you the enthalpy of water fusion. Okay, so let's think about what's happening first. So we're placing ice originally at freezing and room temperature. Well, we know from common sense that if we place ice and room temperature, I'll write it out as a chemical equation. We're putting common sense into chemistry. Look at that. H2O is a solid. You put in room temperature, what's going to happen? H2O becomes a liquid, right? We all know ice melts at room temperature. And the delta H of fusion is 6.02 kilojoules per mole. Delta H is an enthalpy value. Do not get enthalpy and entropy confused. Entropy has values of S Enthalpy has values of H. So we have a positive delta H. If we have a positive delta H, is that endo or exothermic? It's endothermic. So let's think about the system and the surroundings. Whenever looking at entropy problems, the entropy of the universe, we look at the system and the surroundings. So let's look at the entropy of the system first. I always look at the system. Usually I find it to be easier to look at the system first. So we know delta S is equal to delta H over T. Let's write that down. Delta S is equal to delta H of the system over temperature. Well, let's go ahead and start thinking about what we're given. Well, we're given 15 grams of ice, right? 15.0 grams of ice. And ice is just water, so let's find our moles. So 1 mole of water or 1 mole of ice, 18.01 grams. So we now have a certain amount of moles. Go ahead and run the numbers here. 15 divided by 18.01. We have 0.833 moles of ice. Well, now we have moles and we have kilojoules per mole. A delta H value is looking for an energy value. Delta H is directly related to energy. Energy is in the forms of joules or kilojoules, so that's great. So let's take 0.833 times 6.02 kilojoules per mole. What do we notice just happened? The moles cancel and we have an energy value. So we now have 5.006 kilojoules. I'll write that down. 5.006 kilojoules, which is equal to 5,006 joules. So the delta S of the system right now, we have a delta H of 5,006 joules. Well, we know delta S is delta H, the energy over temperature. We know our temperature, right? Our temperature is given to us, 273 Kelvin, which is equal to positive 18.34 joules per Kelvin. Entropy values have units of joules or kilojoules per degree Kelvin. So the delta S, the change in entropy of our system, the ice at 0 degrees Celsius or 273 Kelvin, is 18.34 joules per Kelvin. Great. So now we have 1/2 the problem done. Delta S of the surroundings. Whenever you think about the system, you also think about the surroundings. So the delta S of the surroundings. Negative delta H of the surroundings is equal to temperature of the surroundings. One is positive, one is negative. Go ahead and think about why the system delta H is positive. Well, the ice was at 0 degrees Celsius, right? Let's think in terms of Celsius, because it's a little easier. We know more Celsius than Kelvin. So if the ice was at 0 degrees Celsius at first, and we place it in room temperature, is the ice giving off heat or is it gaining heat? Well, it's going from a solid to a liquid, which is melting, and we know melting requires heat, right? If you want to get some sort of solid into a liquid, you usually have to add heat to melt it down. So this is a positive because we're adding heat to the system. And if we're adding heat to the system, it loses the heat to the surroundings, right? Or sorry, I should rephrase that. If we're adding heat to the system, we are losing that same amount of energy from the surroundings. So if I took 5 liters, we're going to use something very easy. If I took 5 liters of water from a 5-gallon jug and I put it into a separate 5-gallon jug, I'll draw this out. I'll draw this out for you guys. So I have 5 liters of water here, and I have an empty jug. I have jug 1 and I have jug 2. If I take out the 5 liters from jug 1 and put them into jug 2, this would be a positive gain of 5 liters, right? We put 5 liters into initial 0, plus 5 liters. This would be a negative 5 liters. We lost 5 liters from here. 5, give away 5, you go to 0. So in this case, this is a positive reaction. This is a negative reaction. It's giving off. So in this case, we are giving off the energy. We are losing the energy to the system from the surroundings. Well, we already know our S value, or our H value. It's a negative 5,006. We know that from here. But what is the temperature in our surroundings? 298 Kelvin. Right? The system, the ice, was at 273 Kelvin, but the surroundings, the room, is at 298 Kelvin. So we have negative 16.79 joules per Kelvin. And then we know delta S of the universe is equal to delta S of the system plus delta S of surroundings. So we have 18.34 minus 16.79 joules per Kelvin, and you have the delta S of the universe to be positive 1.55 joules per Kelvin. Is this spontaneous or non-spontaneous? It's a positive delta S, so it's a spontaneous reaction. All right, those are the problems that we have lined up for this week. Feel free to go back and work out any of the problems you didn't understand. Once again, always available for questions. I would highly encourage it before the next exam coming up in a week and a half. Other than that, at least today is Saturday. It's really nice outside. Go and enjoy yourselves. Tomorrow is going to be cruddy. So I hope you guys all have a great week. And I will see you guys for the next post.